Let's look at question number 6. It didn't print out well for me this time, so I just rewrote it. What we want to do is we want to answer some questions about a matrix A, about its column space, its row space, and about its null space. So I know the first thing I would like to do is to write A in row echelon form, which means what I'd like to do is zero out the entry in the second row, first column. The Gauss multiplier is going to be -1 divided by 1, which is -1. And that means I would multiply the first row by -1 and subtract it from the second, or multiply the first row by 1 and add it to the second, because subtracting a negative is equivalent to adding. Which means that the row echelon form for A is going to be 1, -1, -2, 1. The first row remains the same. Then when I add the first row to the second, it will be 0 as I wanted, 2, 0, 1. So that's the row echelon form for A. Now I wanted to find the column space of A. After I put A in row echelon form, what I do is I identify the pivots. And in this case, the pivots are 1 and 2. They're in the first row and second row of the row echelon form. And that means that in order to find or write out the column space for A, what I do is I go back to the original matrix A and pick out the columns of A that match the pivots. So in this particular case, the basis would contain the vector 1, -1, the first column, and the vector -1, 3, the second column of A. Now these are not unique, but this is one way that we could find the column space, or vectors that span the column space of A. Now we want to find the basis for the row space of A. This time we look at the row echelon form for A, and the row space is based on the rows of the row echelon form. But we need to describe vectors that span the row space. So actually the vectors in the row space are actually the transpose of the rows of the row echelon form of A. So in this particular case, it's going to contain 2 vectors, both of size 4, where the first one will be the transpose of this row, which will be the column vector 1, -1, -2, 1. And the second vector will be the vector 0, 2, 0, 1. And again, these are not unique. Linear combinations of these will also could actually be a basis for the row space, but this is a mechanism to give us a basis. Okay, now what we want to do is to figure out the null space of A. Now what is the null space? First of all, it's the set of x's such that AX is equal to the 0 vector. So in this particular case, what I need to do is to find the values that make our matrix A times x the 0 vector. In order to do that, what I could do is I could look at the appended system of A, appended by the vector 0, 0. If I put that in row echelon form, that will be the appended system 1, -1, -2, 1, 0, 2, 0, 1, appended with the vector 0, 0. Remember, to get into row echelon form, I added the first row to the second row, so 0 plus 0 is 0, so it works out that way. always anyway. We could append the 0 vector to the row echelon form to find the null space. So I need to find the vectors x that satisfy this. It's going to have 4 components. I could call them chi0, chi1, chi2, and chi3. And since these are the pivots, our solutions are going to have 2 free variables and 2 dependent variables. If I wanted to find the null space, what I do is I pick convenient values for the free variables, which will be chi2 and chi3, and then determine the values for the dependent variables, chi0, chi1, to make sure the solutions will be zeros. So let's see. I want to find 2 linearly independent vectors. So to find the first one, I'm going to set chi2 equal to 1 and chi3 equal to 0, and then I'll switch. To find the second one, I'll let chi2 be equal to 0 and chi3 be equal to 1. Now what do I end up with here? If chi2 is equal to 1 and chi3 equals 0, this first row describes the equation chi0 minus chi1 minus 2 times 1 plus 1 times 0 is equal to 0, which means that we have the equation chi0 minus chi1 minus 2 is equal to 0. Then the second equation becomes 0 chi0 plus 2 chi1 plus 0 times 1 plus 1 times 0 is equal to 0. Solving backwards, I find that chi1 must be equal to 0, which means that chi0 is equal to 2. Would have to be 2 minus 0 plus minus 2 is equal to 0. So one of the vectors in the null space is going to be the vector 2, 0, 1, 0. The other I can find by solving the system's chi0 minus chi1 minus 2 times 0 plus 1 times 1 is equal to 0, and 0 plus 2 chi1 plus 0 plus 1 is equal to 0, which means that chi1 is equal to negative 1/2, solving the system's backwards substitution, by backwards substitution. That is solving this. Substituting in chi0 minus a negative 1/2 plus 1 would have to be equal to 0, which means that chi0 must be minus 3/2. So the second vector that's linearly independent in the null space would be the vector with components negative 3/2, negative 1/2, 0, 1. So that's question number 6.